Hey everyone, and welcome. Today, we're cracking open the organic chemist's toolbox. And what are we trying to build? Well, we're going after ketones. They are, without a doubt, one of the most important building blocks in all of chemistry. So let's get right into it. All right, so here it is, the star of the show, the ketone. Now, what makes a ketone to ketone? It's all about this one specific feature right in the middle, that carbon atom double bonded to an oxygen atom. We call that the carbonyl group. And that little group is what makes ketones so incredibly useful and reactive. You'll notice it's always hugged on both sides by other carbon groups. We just label them R for now. Every single reaction we look at today has one goal: to build this exact structure.
Think of this as our game plan for today. You see, in chemistry, there's almost never just one way to do something. The real art is knowing which tool to pick from the toolbox. It all depends on what you're starting with, your ingredients, you could say. So we're going to explore three of the biggest pathways, starting from things called acyl chlorides, from nitriles, and from those ring structures like benzene.
Okay, let's jump into our first pathway. This one starts with a really reactive molecule called an acyl chloride. The easiest way to think about it is it's a carbonyl group that has a chlorine atom hanging off of it, and that chlorine makes it super eager to react. But there's a catch. We have to be really precise with how we handle it.
So here's the problem we need to solve. Your first instinct as a chemist might be to grab a really common, really powerful tool called a Grignard reagent. But the thing is, it's too powerful for this job. It's kind of like using a sledgehammer to hang a picture frame. The Grignard reagent just goes too far, it overreacts, and you end up with something that isn't the ketone you wanted. So we've got to get a little more clever. And this is the clever workaround. What we do is we take that powerful Grignard reagent, the RMGX you see there, and we react it with cadmium chloride first. This step essentially tames the Grignard. It dials back its reactivity just enough. What we end up with is this new molecule, dialkyl cadmium, which is our crucial middleman. It's a temporary stepping stone that has the perfect Goldilocks level of reactivity for what we want to do next.
And here's the magic moment. The alkyl group from our dialkyl cadmium comes in and performs what we call a nucleophilic attack. Basically, it's really attracted to the carbon in the carbonyl group. And as it attaches, it gives that chlorine atom a little nudge, and the chlorine is more than happy to leave. We call it a leaving group. The result? A perfect swap. And boom, there's our ketone. It's just a really elegant and controlled way to get the job done.
All right, on to tool number 2 in our toolbox. So what if you don't have an acyl chloride lying around? What if your starting material is a nitrile? Well, a nitrile is just a compound with a carbon-nitrogen triple bond. And it turns out there's a great pathway designed for exactly this scenario.
So, look who's back, our old friend, the powerful Grignard reagent. But this time, unlike with the acyl chlorides, its raw power is exactly what we need. It goes right in and attacks the carbon of that triple bond, breaking one of the bonds and forming this temporary structure called an imine salt. Now, we're not at a ketone yet, but that's okay. The important thing is we've built the basic carbon skeleton that we want. We're halfway there.
Okay, time to finish the job. For step 2, all we do is add some acid and water. This whole process is called hydrolysis. And what it does is pretty amazing. It completely cuts off the entire nitrogen piece of the molecule. Then, in a beautiful little swap, an oxygen atom takes its place, forming that classic carbon-oxygen double bond we're after. And just like that, the imine salt is gone. And voila, we've made our ketone.
Let's move on to our third and final headliner reaction. This one's a classic. It's got a famous name, the Friedel-Crafts acylation. And this is your go-to method for one very specific but very important job: sticking a ketone group directly onto an aromatic ring, like benzene.
Now, this whole reaction hinges on one key ingredient, that catalyst you see over the arrow, aluminum chloride. You see, if you just mix benzene and an acyl chloride together, nothing happens. They'll just sit there. But when you add a Lewis acid catalyst like this one, it acts like a chemical matchmaker. It supercharges the acyl chloride, makes it way more reactive, and allows it to attach right onto that benzene ring. What you get is a special kind of ketone called an aromatic ketone.
So those were the 3 main highways, you could say. But a real chemist toolbox is way bigger than that. There are tons of other specialized reactions for making ketones and their close cousins, aldehydes, from all sorts of different molecules. Let's just take a quick peek at how diverse this toolkit can really get.
For instance, check out this chart. A super common method is to oxidize alcohols. But here's the really cool part. What you start with completely changes what you end up with. Look at the middle row.
If you start with what's called a secondary alcohol and you hit it with the right oxidizing agent, you get a ketone. Perfect. But look at the top row. If you start with a primary alcohol and use a similar reagent, you get an aldehyde instead. It just goes to show you that precision is everything.
And trust me, it gets even more specialized. You don't need to memorize all the names on this slide. Just appreciate the variety for a second. Every single one of these reagents, from D-ball H to ozone, is designed to do one very specific job on one very specific type of molecule. It's kind of like having a unique key for every single lock in a giant building. It's all about having the exact right tool for the transformation you're trying to achieve.
All right, enough of me talking. We've gone through the theory, we've seen how these tools work. Now it's time for you to put on your own virtual safety goggles, because it's your turn to be the chemist.
Okay, check out these 4 reactions on the screen. Each one uses one of the exact principles we just talked about. What I want you to do is look at the starting materials, look at the reagents over the arrow, and try to figure out what the final product is going to be. Go ahead and hit pause here, really think it through, give it a shot.
So, before we go, let's just do a quick recap of the big takeaways. These are the core formulas. For acyl chlorides, you tame a Grignard with cadmium. For nitriles, it's that 2-step process: Grignard attack, then hydrolysis. And for benzene, it's the classic Friedel-Crafts reaction with a Lewis acid. Think of these as the 3 fundamental recipes in our ketone cookbook.
And that's a wrap. We've just stocked our chemical toolbox with some really powerful, really precise methods for making ketones. So, the final question I want to leave you with is this. Knowing how to build this crucial piece, this fundamental building block, what larger, more complex, more amazing molecules could you imagine building? Think about all the possibilities in medicine or new materials. What problems could you solve? Thanks so much for joining me.